this one and then clip Raman's one on as well.
Wait, this is. Do you want me to clip my side? So you said?
Yeah, like both.
Oh, both. Wait, how can?
Yeah, this one you just I don't know, clip it on or whatever.
Wait, Raman, here.
Where's the other?
Try.
Yeah, keep it.
No, wait, we're just testing first.
Oh, you're testing.
Yeah.
Okay, do you wanna?
So, yeah, go for it.
All right. So, what's the ETH price for this year?
What's the maximum? It's a super cycle. Super cycle. We're going up to the moon. 10K minimum, and 100K is my sell price.
Perfect.
Sell target.
Perfect.
Not a financial advice. Not a financial advice. Do your own research.
Okay. We are at the only dev meetup not the only, but one of the dev focused meetup where we said we don't talk about price action, and that's how we start.
USDC is going to pump. Yeah, I'm sure. Buy USDC and USDT. Buy all stables. They're definitely gonna give you 100x.
The ticker is ETH.
The ticker is ETH.
Why is there no sound on this one? I'm not hearing it. You want to just talk into the mic again?
Yeah. I mean, wait. Does it actually play any sound? Is the laptop playing any sound?
Yeah. The volume is max.
Wait, can it? No, usually there's a dot 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 dot. Oh. It's going through it. Go to your sound setting. Just sound. And your laptop's gonna run out of battery if you don't charge it. Wait, spot it. Sound.
Yeah.
See? The sound's not going through there, right? Output. You output there. It's going through it. Go to your sound setting.
Okay, awesome. Thanks. Alright. That's an embarrassing start to a live stream.
Wait, so you're getting it?
Yes.
Wait, you sure you don't want it?
No,
you don't want to plug it in?
Now it's good.
No, I mean the battery.
Oh yeah.
Like, cause can you just run a wire through? Because you really gotta. You're not gonna last.
I didn't bring my wire. Do you happen to have an extra MacBook charger?
Yeah. I mean, not just a USB-C one.
Yeah, just a regular, whatever works here.
The only thing is, where is the plug? I mean, there's one here, but it's kind of trip hazard. Is there anything under you?
No, I'll just plug it in here.
Wait, is there one? Okay, yeah, that's what I meant.
You need the power supply still, or just?
I did not bring mine. Sorry.
Yeah, but the actual plug that goes right
Wouldn't stick, huh? It wouldn't stick.
The what's it called?
Wait.
It doesn't.
Yeah.
You should try it.
Oh no. Does it? Wait, let go. Oh shit. No, because it doesn't.
It's just this thing over here.
It's not sticking. Here. How long? Okay, it's not that long. Wait, use the tripod. Can you? Oh, there you go.
Feeling generous today.
Awesome.
At the risk of my camera dying, but.
Oh. Can your camera use this one then?
Hey, do you think you could use this? Or this?
I mean, I'm on a power bank, but maybe it will.
Okay. Well, you know what? By the time if that runs a battery, this could probably charge because normally these things charge pretty quickly.
Okay.
So yeah. Just.
So I still owe you the wire. Yeah.
Okay.
Yeah, go for it.
All right. right, so I think I'll start then. Does the first speaker have a mic? Does the first speaker have a mic? Wait, is this?
It's not JC. So
No, it's Eric. Eric. Is it Eric? Sorry, from Malaysia. I just remember the. Sorry, Ethan. Yeah. So I think you should have a mic first, right? So you give him the first mic.
No, as in like you're just trying to look.
Wait. Why do we need two mics?
Because one is Roman's.
Okay, I didn't realize. I thought they were two. I thought they were just the same source but different. Okay, got it. Okay, well I guess I'll start. All right. Hey guys, can I get your attention, please? We're going to start. So maybe we're behind just 15 minutes, but that's okay. It's well within our buffer. So just want to say welcome. Can I just get a show of hands on who is not based in Singapore here? That's not based in Singapore. Okay, that's a good like 50%. Awesome. And I guess the rest of you are based in here. For those based here, any of you been to any of the talks, or do I look familiar, or Brendan or Raman familiar? Any of you guys have been at talks before? No? Okay. So I think most of you are pretty new to everything, which is good. So here's the agenda for today. We passed registration. Now we're on the introduction. Then we'll have 4 speakers from 4 different countries and 4 different projects. And we'll have Brandon from Injected to give us a bit of a spiel from his company. And then later on at the end, we'll finish with some networking. We are get kicked out at 5 o'clock, but I'm pretty confident we'll have a lot of time for people to network, get some kopis, and that's coffee in Singapore speak, and some tea, and some Singaporean pastries that we've got prepared for you. So it's going to be a good day. Good afternoon. So just a little bit of about us. I'm one of the organizers for Solidity Singapore and Crypto SG. So Solidity Singapore is a blockchain developer-focused meetup. So I think we do a meetup once every couple months. You were laughing because supposedly we have been a little bit lazy, but that's all right, And I'm also, I'm also one of the organizers for Crypto SG. So it's almost like a where we straightly talk about programmable cryptography, or applied cryptography in blockchain. And then we also have dApp developer from DADC, which Brendan's one of the organizers. So, and that's focused on dApp development. So, yeah. So here's, in case you want to join our community, especially for those in Singapore, you might want to come back here. And even for those who are not from Singapore, you might want to look us up again next year, because this is like our second time doing an event at a pre-token2049. So it's a bit, what we do is also a little bit different than what Token is about. If you guys have been to Token, you guys will realize that that's a lot about the finance side, the trading side, the fundraising side of things. Whereas us, the 3 organizations or meetups that I mentioned, are mostly focused on developers. And yeah, so I mean, even though I'm not from Singapore, I've only been here for a couple of years, but I was quite, when I first got here, I was quite amazed at the amount of tech talent that actually Singapore has, which is not always so obvious, because the finance side and all that kind of stuff kind of is very loud, right, compared to the developers. So we always welcome, developers or people who are aspiring to be developers, and even cryptography researchers to come and join us. So. Lastly, just want to give a shout out to Injective, which is Brendan's company, for sponsoring the F&B today, and to SMU Blockchain Club. So SMU is the Singapore Management University, the venue that we're in right now, for giving us this venue. Because venues are very tough to get this week. It's probably the toughest week, the busiest week in Singapore by far. I think most Singaporeans would agree with me.
I'll just add on that we tried to do one last year, it didn't happen because we just couldn't get a venue. So count yourself
Yeah,
lucky.
or it's very, very expensive. Yeah. So we're very happy. We did book like about 4 months in advance, so and we still couldn't get one on the weeknights. But yeah, yeah. So yeah, if you're in Singapore again, we organize these events every couple of months, and it's mostly in person. So we don't do too many online. But if you're in town, do let us know. And with all that out of the way, let the talks begin. So our first talk will be from Ethan from Space Range, so from Malaysia. So please, Ethan. 10 minutes, and then 10 minutes talking and 5 minutes Q&A, and then 5 minutes transition. So we'll give you a signal.
Sure.
Yeah. So if you just click all these on, that's the bottom. Yeah. And these two are the top. Yeah.
Oh, both.
Yeah, both. Yeah, it's a two-part. There's actually a YouTube live stream that we're doing. We'll post the link on the Luma in a bit. So.
All right. Hey guys, my name is Ethan. Give me one moment. Let's see, where's my mouse? Okay. All right, how are you guys doing today? Good? Okay, I hope my internet doesn't die on me. Okay, never mind. So just like before I get started, how many of you guys are technical? Just so that I can gauge. Okay, are you guys like new to Web3 or like quite deep? New? Anyone new? Okay, cool. So I think like you guys are probably kind of familiar with crypto already. But yeah, like today's workshop, I'll just basically show you guys how we can build with Cosmic RNG. So anyone here familiar with random number generators or like Chainlink VRF? Anyone heard of it before? Yep. Okay. So basically, like if you want to do something on chain, and you need like a random number generator, for example, like a lottery or any other kind of application, you need this kind of like RNG. But what we are building is a cosmic RNG, which is basically coming from like cosmic radiation. So it's not actually like pseudo randomness, which is usually like derived from your CPU and stuff like that. But yeah, just a brief introduction about like what Space Computer is. Space Computer is essentially building a cryptographically secure compute protocol for any blockchain. So what we're doing is we're launching TEs into space. TEs are trusted execution environments, and we're going to have a network of these space TEs. And essentially, like all of these TEs can run smart contracts. And we're also building an economic layer where you can essentially have a marketplace and people can do payments in order for you to like host smart contracts over there, or even like just run them. So why space TEs, and also like why now? It's because like if we launch computers into space, it's technically more secure. There's a layer of like physical isolation. If you are hosting a server on Earth, it's easy to break in and like destroy that data center, or maybe earthquakes or like some natural disaster. But in space, theoretically, it's much more difficult for you to get out there and try to like take down one of those satellites. And also like within the past 2 years, we've actually launched more things into space than we ever did for the entire like century. So yeah, that's why we're doing things in space. So right now we only have one space TE, and in order for you to communicate with it, you got to use our gateway called Orbit Port. So you can call it through an API, you can use an SDK, but I'll show you guys how to actually use it on chain. So we have sort of like a two-tier architecture. Because of the latency of like communicating with like space satellites, it wouldn't make sense for you to actually like execute transactions in space. So think of the space layer as your L1, and we will find like a suitable L2 in order for us to like handle all of the transactions and then just like bundle everything and push it back into our L1, which is our celestial chain, and essentially like that will be your source of truth. So yeah, like this is a little bit more on like CTRNG. It gets a little bit technical, but basically the satellites right now are run by a company called Aptos Orbital, and that's where we're getting the randomness from. And then basically like we'll just aggregate all the values, batch them, and then push them into like an IPFS beacon that you can retrieve these values from. So yeah, there's a lot of things that you can do with Space Computer and even with like CTRNG itself. And if you're wondering about like the pros and cons of CTRNG compared to like VRF, one thing is that like we are, as I mentioned, true randomness compared to like pseudo randomness. Space-based infrastructure, again, we have the physical isolation, and we're running everything in a TE. So even if the host or the hypervisor is compromised or malicious, you can be rest assured that your everything running within the TE is still secure. So yeah, I've not done a workshop or attended a workshop ever since AI became a thing. So I don't know how people react to live coding. Does anyone actually want to code together, or are you guys just listening? How many is going to code? Because I only see like a few laptops. Okay, so I'll show you guys how to interact with it. For those who are not coding, feel free to just listen along. For those who are coding, once you guys get the hang of it, feel free to just like vibe code something. I may not touch on the front end depending on time, but yeah. So back to our orbit port and CTRNG, there's actually a few ways to interact with it. I know it's a little bit tiny, but I'll sort of like just explain it for you guys. One is through API, so you can call orbit port directly, but you need an API access key. You can get that from like our Telegram channel. I'll give you guys a QR at the end, or you can get it directly from IPFS. So again, we bundle and push all of these into IPFS every minute. So technically, like even without the API, you guys can get it from IPFS. But do take note that it takes 1 minute for it to refresh. But on orbit port, every time you make a request, you get a new random value. And then lastly, on-chain. So we are partnering with eOracle, and eOracle is basically going to host a network of data validators that pull in all of these values, aggregate them, and then push these values on-chain. The entire infrastructure is still being set up. So for this demo, we actually have a sort of like a replica of what it will be like once eOracle fully supports us. So the interface, everything is the exact same. It's just that there's certain things that are not optimized yet. So we have a pool-based Oracle, and so like for Oracle systems, for those who don't know, there's push-based and there's pool-based. Push-based is when you're requesting for like a random value and then you can get it back. Pool-based is like the data is already there, so you're just pulling, you're fetching data from it. Most of the time, like Chainlink VRF, you would use a push-based Oracle. But again, because the infrastructure is not set up yet, so we have a pool-based Oracle. So it's a little bit funny because it updates every minute, so you only get a random value every minute. But you can always like add in your own entropy, like your timestamp or anything else, just to make it more secure. Okay, so for those who have their laptops out, feel free to scan the QR, and yeah, you can basically redirect you to like GitHub. So once you guys got it, then I'll sort of show you guys the code. All good? Okay, let's move on. Is it too tiny? Should I make it bigger?
Space Computer orbit port demo. Is that the one?
Yeah.
Okay.
Oh, did you guys go to this one? No? Oh, my bad. Okay, never mind. This one works too. Okay. So feel free to clone this repo. So once you clone it, you essentially have like a dap folder and a front end folder, and that's where we'll sort of be building things out of it. Yeah. To give you guys more context as well, we have a repo called like OrbitPort Oracle. This is not the finalized version, but basically like if you scroll down, you'd see the deployed contract address. Right now we only have it on Arbitrum Sepolia, but of course like in the future we'll support every other chain. I'll show you guys what it looks like here, so you can see that there is sort of like data being updated every minute. And yeah, like if you want to read from these contracts, you can basically just I don't think I need to connect, but get feed. There you go. So right now we're using feed ID 0 because we're the only ones pushing to this contract. And so like if you query it, then you get a uin256 random value that you can do anything with. Yep. Okay. Any questions so far, or like should we do it at the end? Okay. How many more minutes do I have? Okay, that's enough time, I think. Okay. Cool. So for those who are coding along, we can go into the dep folder. This is using Foundry. Another thing with like workshops is that you always have to like set up all the tools. So if you guys don't have like Foundry or anything else, you can set it up after this session, but I will show you guys what you can do first. So this is just a dice game, but of course you can do anything else. It can be a coin flip, it can be like picking a number 1 to 10, it could be anything. But yeah, like basically all you got to do is you have to connect to eOracle's feed manager. And so like if you have Foundry installed and you run install, it should install everything straight away. So that includes like this interface here. I'll show you guys what it looks like if I can open it. Okay, so this is basically like the standard interface for eOracle. I'll probably make it bigger. Any like Oracle feed data that's like pool based that we push to eOracle would be basically like interacting with this contract. So whatever we're doing now, even though it's not on their infrastructure yet, but once we do migrate it over, it will be exactly the same. So yeah, there's a lot of things like within this contract, but again, it's like coming from eOracle. So you have to like connect to it. And one way is like through the constructor. So we'll just initialize the feed manager itself. And so like you can do all sorts of things that you want. So for example, like let's say I want to create this function called bet. So thanks to AI, I can code at the speed of light. And like, yeah, so you can just store your bets. But like, of course, customize this function as much as you like. I'll show you guys how to get the random value. So let's say I have a function called resolve. Oh, wow, there you go, AI. So yeah, all you got to do is just IEO feed manager dot price feed, and then yeah, basically like we're storing the price feed data itself, and we're getting the latest price feed, and the feed ID is 0, which we're storing up here. So once you have all of that, and then like again, like because I'm doing a dice roll, so it's between 1 to 6. But of course, like if you want to do like 1 to 10, it could be anything. And then like yeah, that's basically it. You can retrieve your random values. In order for you to deploy this, we would have to go to the deploy script. So inside here, and you can just plug in the address, which is actually like this address. And yeah, like you can just run forge. Oh, there you go. So you can just do like forge script, forge run script dice game. console game, and then you can pass in the RPC URL, which is from Arbitrum Sepolia, because we're already supporting that. And then after that, like, you basically have a dice game deployed. Yeah. So I know it's a really quick demo. If you guys have any questions, feel free to ask me after that. Oh, you don't get the DApp? You don't have a DApp folder?
Is it on Space Computer account or where is it?
Yeah, so
In the live stream, I posted the link to the repo that you need.
In the live stream.
this CTRNG DApp demo.
So in Luma, John has already put the live stream link in there. So I'll be doing live updates throughout.
Yeah, but if you want to test it out on chain itself, best way is through like going to the block explorer and just clicking it.
Can I ask a question?
Yes,
So
sure.
you mentioned that you have one satellite with the TE and it's writing to the smart contract. So
Yep.
double question, what permissions do you have to write into the TEE or for any device, I should say,
Yep.
is there an authentication to write into the smart contract? And the second question is, if there are multiple, then how do they affect each other? Do you just get more numbers, or do they like hash of a hash?
Okay.
What happens?
So when you mean like writing, do you mean like to this smart contract or to the TE?
Well, whichever. Like, so you've got a random source and you're
Yep.
inputting into this contract, and then someone pulls from this contract.
Yep.
So when you have two devices writing into it, right? The second one.
Yeah.
Right. How do you know if that second one is a legit source?
Yep.
Right. And then secondly, if there are two, then what happens to the random numbers? Are they like both inputs used to compute the output, or?
Yeah, that's a good question. Okay, so for the first one, so we can see this data validator here. So basically, like, that data validator is just doing a query using like our SDK into the satellites. We're getting the random value, and then after that, we're just pushing that on chain right now. And in your question of like having two satellites, we haven't actually decided what we're gonna do about these two. The thing is, because cosmic entropy means that it's technically somewhat non-deterministic, but there is a way to validate that the randomness that we're getting is from cosmic entropy itself. There's a certain library that we're using to do that validation. I can't remember what it's called, but yeah, we can either like hash both of them together, because we have the aggregator right here, so we can either like hash all of it together and just push it. But one thing that we're also doing on our IPFS now is that we're pushing all the CTRNG values. So every minute you can see 3 values, but in the future, like, it could be even more. Cool. Yes.
I'm not very techy, but so excuse me if my questions are stupid, but I have 2 questions. Firstly, how do you legitimize, or how do you say, are there trade-offs for putting the main L1 into the space worth it? Worth the latency from here, etc., the cost? And secondly, if you are going to do something like DeFi there, won't it give advantage to anyone who launches another space computer which interacts with your DeFi and has lower latency than?
That's a good question. So the thing is that like what I mentioned earlier as well, most of the execution will actually happen on the L2. So the L2 could be anything like Base or Arbitrum or any other like protocol, and then we would actually push and bundle those values back into our L1. So ideally, we would be creating our own L2 as well. So for example, like using Arbitrum stylus or anything else. And then after that, we will actually just push those values to our own L1. So most of the settlement just happens on the L1, but latency wise, because that's gonna be on the L2 side, so like it wouldn't affect whether you have a satellite or not. Did I answer all your question? I feel like I missed one. No? Okay. Yep.
So one question is how to guarantee liveness of the
of the L2 itself.
Yeah, for example, suppose I use the application for guarantee. The random number is really frequent, constant upgrade. And second, actually,
Yes.
is related is how to guarantee there's no from like running attack, so that maybe because that needs option to submit it, so I can know like what's the result will be. So I probably will delay or maybe run
Yep.
ahead so that I can manipulate the random number.
Yep. Yeah. So again, similar to like the answer for Brandon is that there is a way to do the validation of the randomness through a library. But one thing is that we're also doing a threshold signature cryptography in order for us to actually perform validation that these values are coming from our satellites itself. But that's in the roadmap and it's not live yet. So right now, we're doing a lot of assumptions. The assumption being that since we are the only ones with the randomness, so we're not going to act malicious. But again, in the future, there's going to be a lot more providers for these TEs. Any other questions? Yep.
Yeah, so like considering the complexity, like what are the actual use cases or like real world?
In terms of CTRNG or?
Yeah, like with all of this like complexity of ensuring that the value is consistent. Like in real world application.
Yep.
What kind of application would this be perfect for?
Yeah, I think the biggest one is still in terms of security. So like if you are familiar with like threshold cryptography or like creating like private public keys, most of the time like you would need a source of randomness in order to generate your first pair of keys. So like that is what ideally we want to provide. But again, space computer is a protocol itself. So we see ourselves as a SaaS company. Because in the future, all of the satellites that are going to be launched into space won't necessarily come from us. So we will focus a lot on the consensus, the execution layer, essentially like treating ourselves as building a chain or a protocol. Yeah. Any other questions? Yes.
How do you deal with cosmic radiation in this case? So one of the issues of doing computers in space is that there tends to be bit errors. So if you're trying to do something higher value than just random generation, like the physical construction of like the computer actually matters.
Yeah. That's actually a good question that I have no idea how to answer because sadly I don't engineer the tech. But I will get an answer for you and I'll let you know after this. Cool? Thanks everyone.
Well, a lot of questions, but if there are more questions, feel free to talk to Ethan after this.
Oh, let me really quickly give you guys the QR.
Oh yeah.
Okay, so Telegram is here. Really small.
Put it on your
Blame the designer. I don't have control over the slides. Yeah, I'll just take a whole photo. Cool. Everyone got it? Yes.
Oh, there's a.
So, like this?
And Ethan will still be around until the end of the show. Yeah, in case you want to ask more questions. But, thanks again for giving So next up we have Chijo, who's going to talk to us about scaling Ethereum.
Yep. Okay, cool. I can start? Okay, cool. Hello, everybody. My name is Chijo. A quick introduction of myself. I have been in this space about 7 years. Before that, I was a software engineer at Facebook. I'm working on their infrastructure. So that's why I'm particularly interested in Ethereum infrastructure, especially Layer 1, Layer 2, DA. Get a couple of supports from Ethereum Foundation, including personal grant from Vitalik, and also issue storage. There's a Layer 2 solution to scaling Ethereum, and also a couple of grants for OpenStack.
So today I'm going to share some of our work on Ethereum Layer 1 scaling, especially with some latest technologies called block level access list, which enables parallel execution, and also EVM compiler, which is able to compile the EVM contract code to the native code and then execute directly, with some experimental results on Go Ethereum. And the ultimate goal is try to answer the question that can be achieved 100x block gas limit of current Ethereum. Right now it's about 45 million, but we want to achieve 100x in the future Ethereum scaling plan. So especially from the execution side. So there's one big change of Ethereum roadmap this year is that Ethereum is not only trying to scale their layer 2, but also aims to scale the L1. In order to address a couple of issues in terms of, for example, liquidity fragmentation, and also some incentive alignment issue that a lot of people are discussing. So the near plan is to increase the gas limit, which is basically adopt a big block philosophy, so that we are able to increase this gas limit from, for example, 36 million to 46 million. Actually, it is now running in this with this number, and there's a concrete plan to increase this number to further to 60 million or even 100 million. And so the question is, with all these near plans, what is the ultimate goal that we can achieve with Ethereum current, for example, execution, EVM smart contract, and also, for example, MPT, the tree. And what is the ultimate boundary of the Ethereum L1 block limit? For example, suppose if we want to achieve 100x, that means that we need to have 4.6 giga gas per block. So this is a pretty large number. I will explain later. So before we dived into the real number, let's look at how the current situation is. So this is one gas that latest gas I run on top of a pretty powerful machine with 16 cores and also RAID 0 NVMe SSD. And so it can achieve about 300 megagas per second. Actually, there are optimization has been done recently. So actually, early this year is about 150 million gas per second. So it's about twice because of recent optimization. However, the Ethereum consensus require all the nodes can validate the corresponding execution result, which means that it has to up to 4 seconds to verify all those transactions and sign, and also be able to broadcast and also sign the corresponding attestation in the following time slots. So which means that we can have up to 1.2 giga, which is 4 times 300. That's clear. So that is the current limit of the, especially for Go Ethereum client. And for other clients, maybe a little bit better, but the number is also very close. So which means that we are only about to support 12,000 Uniswap V2 swaps per second. So which means that we're still a little bit far away from the ultimate goal that we can scale Ethereum 100x on layer 1. So one quick question is that can we also rely on moral law to basically increase these limits, just sleeping on our bed, and then the hardware will automatically accelerate all the execution, and also both in terms of memory and disk and also bandwidth? The short answer is no. The reason is that the moral law is not yet working these days. Everybody knows that the frequency of our CPU is capped by about 4 gigahertz around 2005 year. The reason is that we cannot build such small number of the some limits or physical limits of those transistors. However, another observation is that we have called modified Moore's law, that showing that if we take into account the number of cores per CPU chips, actually it still applies. So this is a multi-core area. Actually, the line is still almost double in 18 months. And so that means that we are able to also employ this modified Moore's law to also improve the EVM execution. Unfortunately, it's not, because EVM execution is just sequential, which means that we can only harvest the benefits before 2005 because of the CPU the speed limit. So because of this, Ethereum Foundation also called developers thinking about how to employ the multi-core processing to improve the Ethereum EVM execution performance. So the most recent update is called block level access list. It was introduced in EIP 7928. Actually, 2 years before, we was proposed a similar idea via a ESP academic grant to say, hey, we should investigate how we are able to parallelize EVM execution. Actually, our idea at the time is not only be able to apply to layer 1, it can also apply to layer 2, so that both layer 1 and layer 2 can benefit from this multi-processing. So the general idea is to add a called access list in the Ethereum block to tell what are the locations of all the transactions we'll access in this block, including the address, including the slots, the storage slots, and also may include the corresponding value. For example, what's the value corresponding to those locations. So the benefits of block level access list is that because we are now running the Ethereum in a sequential way, so there's a significant latency from the I/O readings, because every time you just issue one I/O, wait, and then wait for the I/O back. So in the early result, actually this is the result of the early this year, is that 80% of the EVM execution that is waiting for the I/O response. So that takes a significant amount of the EVM execution. So at the same time, actually the modern disk, like for example, this is just a disk that with about $100 US, can easily offer like 10s or even 30s parallel IOs without sacrificing just a small sacrifice of the latency, but almost retrieve the really high bandwidth. Actually, this can be even more, but just for the illustration purpose, like we can actually issue much more parallel IOs. So, which means that if we are able to fully utilize the parallel IOs, then we can easily achieve 10 times or even sometimes 20 or 30 times improvement on the EVM execution on reading IOs. And so with the introduction of the block level access list, so a significant change is that now we are able to using the BIL information so that we can first read all this data parallel from the database, so that we can almost, I will show the data later, eliminate corresponding read IOs in the EVM execution. And second, with a slightly improvement of this BAL, we are also able to run those transactions in complete parallel. So for example, suppose we are able to use, for example, 60-core CPUs, then we are expected to achieve 10 times of performance using just very widely adopted like commodity PCs. So we implement all these ideas on top of Go Ethereum, both in terms of parallel I/O and also parallel execution, and then we study how much performance improvement can be achieved using these ideas. So it's using pretty latest machine and with a very high performance SSD. And also we make sure that every test is fair, so have to clear page cache, and otherwise the cache may speed up the corresponding results or the second results. And also the key result is that, so if without, for example, the BAL with parallel IOs, we can observe that the IO still takes a significant time. That actually is the optimized guess, which takes about more than 50% of the execution. So with the parallel IOs, we can reduce this number to less than from 1 to the 10x, and right now the number has become less than 10%. And at the same time, so this is still experiment on sequential execution. So the execution now becomes the biggest part of the EVM block processing. So the next experiment is to using parallel execution with some additional information of block level access list, so that now we can parallelly execute those transactions and further reduce the time. Right now we can achieve about 6 seconds in 500 recent produced blocks. And so with all this, we also get do some experiments. Especially, we found other parts of the EVM execution that is meant to calculate the Merkle root of the execution, so that we are able to recompute the hash root of the world hash, which will take a significant time. So we then say, hey, whether we are able to amortize those costs by using large number, that's 10x block class limit. By basically, the simple idea is just aggregate 10 blocks. So rather than verify their hash roots for every block, it will basically verify the hash root for every 10 blocks, and then amortize those costs on the hash root computation. And then we are able to achieve currently 1.2 gigagas per second, which times 4, which means that we are able to use this technique. We are almost be able to satisfy the 100x block gas limit of current Ethereum. So this is a pretty amazing result. So besides block level access list, we are also considering another further question. Is that can we further accelerate EVM execution? Because now this part seems to become the bottleneck. Recently, there are a couple of the latest ideas that is flying around in the Ethereum ecosystem. So one direction is called RISC-V, which basically to using the RISC compile the smart contract into RISC-V OP code and then run natively on some machines. That means that we need to transpile existing EVM bytecode and also need some new gas metering. The big direction is to still support the EVM as the execution engine, and then compile them to the native code, for example, x86. So there are a couple of famous ones, for example, REVM-C, EVM1, and also EVM MLR. And unfortunately, when we are trying to evaluate the corresponding result on top of gas, we cannot find the handy compiler, EVM compiler for gas. That's why we create called Go EVM-C, which is an EVM compiler that can be used by Golang, for example, Go Ethereum. So that now we are able to compile smart contract into LLVM-IR first. That's the intermediate representation, and then convert it into a local binary so that we can achieve the native performance on top of our local machines. So this is an example of how the intermediate representation in the LL format looks like. And so the couple of design goals. So first of all, it can be compatible with gas, so that we are able to easily be integrated with gas to evaluate all the performance. And also, it is able to minimize the recompile cost for EVM upgrades, especially if we implement all these we call unstable OP codes. Then we have to recompile them every time. And so, and also in terms of optimization. So we just open source the repo, and our performance is pretty promising these days. We shows that compared with the Go Ethereum, we can achieve about, so this is the Go Ethereum, this is our optimized result, about 3 times performance improvement on top of Fibonacci sequence computation. Okay, since we have a limited time, I will skip some slides and future work. So really happy to share our recent work on all those Ethereum optimization, and also would like to answer some questions if you have. Thanks.
Yeah, I guess this approach is a little bit in tension against, having people be able to prove on a mobile device or something, like sort of light clients and stuff like that. How do you? I mean, if someone were to run this, they need that super fast compute
Yeah. So actually, there's more precisely, that's called ZKVM that aims to basically do the off-chain proving and off-chain computation, and then be able to prove easily on top of even on a cell phone or any other like mobile devices. So I think there's a lot of involvement. For example, if they recently had a called Lean consensus, which one of the tasks is to try to achieve that goal. So, but for near short term, actually, still like Ethereum, if we want to be able to immediately, about 1 or 2 years, to be able to increase this capacity to 10x or 100x, this is some technology that we should adopt. And second is that even compared to cell phone, it's relatively more expensive. But all this, for example, this experiment built on top of we are built on, but it's about $100 per month machine, which compared to the validator cost, which is 32 Ether, that is almost
I was somehow getting the impression that you would cost $20,000 setup to run a machine. So,
No.
but in order for this to work, all the clients would need to be running this instead of like they would need to have a certain spec machine that would be sort of a minimum spec machine they would need to run, right?
In order to use all this. Yeah, so all this upgrade spec will be incorporated into all the clients.
Yeah.
So that's why there's other clients, for example, RAS. So RAS, Zig, they are also implementing their features. But the point is, like, to our best knowledge, we are the first one to evaluate this comprehensive results on top of Go Ethereum, which is the one of the largest client on the adopted by the other people. So yeah.
All right. Thank you very much.
Yeah, feel free to ask me more questions after the talk. Yeah. Cool.
It's very deep pockets. There you go. Are you presenting?
Yeah, just talk. All right, hi everyone. It's me again, Brendan. So thank you everyone for coming today on a Saturday afternoon. I just wanted to say a few words about Injective, who is sponsoring today's event. So like I said earlier on, there's drinks and snacks at the back in the corner over there, and then there's also plush toys and a bunch of other swag in the boxes right at the center at the back. So what is Injective, right? Injective is a layer 1 network that is started off as actually a perp DEX, perpetuals trading platform, and then they decided to make a blockchain out of it, right? And then so it was its own L1 blockchain that had its own set of like trading or finance related APIs, and then that grew bigger. They added CosmWasm, right, which is a smart contract platform that is familiar to the Cosmos network, right? Developers on the Cosmos network. And then very recently, just I think about 2 months ago, we launched EVM on testnet, and as of this week, we're on EVM mainnet as well. So yeah, you can do your standard Solidity smart contracts, etc. All of that you can do it within Injective as of right now. So yeah, give it a go. And if any of you are developers and would like to build on an EVM network, a new EVM network, but also have like really cool features that you can't really do on other EVMs, then talk to me. And by really cool features, I mean, for example, right, if you want to create a decentralized exchange, a DEX, right, pretty much the go-to way of doing it is to use an AMM, like an automated market maker formula, and that's kind of what Uniswap does, and Curve does something similar as well, but not exactly the same. But these are all like a different way of creating a market compared to something which you see, like say, in Singapore Stock Exchange or Wall Street, that kind of thing, where they use an order book, right? So this is where you have buys and sells, and then you line them up, and then whenever the buy price meets the sell price, then you get a trade, right? So that kind of order book is almost impossible to run in right in Solidity, like for gas cost reasons and a bunch of other things. So
So instead, we've got our own on-chain order book. So you can like create a order book, right, through native APIs, and you can also access that through smart contract code, like in Solidity by precompiles. So if that sort of thing is really interesting to you, then come talk to me. Right. That's it. I just had a really short spiel, and now on to our next speaker, who is going to be David, right? Who has, I think, by my count, not slept for about 36 hours because he had quite a trip getting here. So please give him a round of applause.
I'm just trying to connect the internet. Is it different Wi-Fi that's supposed to be on? Let's get the screen working first. Oh, okay. Shit. It wasn't. Even it wasn't working. Should it be connected?
If you want to use that screen.
Oh, no, no. Right.
Just press allow. That's for this one. And then. Alright, it's on the screen. Your browser is on the screen.
Okay. I think I connected to my phone's hotspots, but okay, I think we can use this that I opened previously.
Alright, it's on the screen.
Yeah, okay. Okay, hi everyone. I'm David. So I used to be an engineer at Consensus, after which I left Consensus to start working on Bonadocs through like the Consensus Fellowship Program. So like post-leaving Consensus, I joined Fellowship Program. You can't hear me? Okay.
Alright, pardon us through these AV.
Alright. Yeah. Okay, so I currently work on Bonadocs. So Bonadocs is basically like a postman for smart contracts, basically. But in this talk today, I'll be talking about building applications, right? So basically, in engineering teams, right, while building like the front end, you are mostly torn between either integrating directly, using like VM or ethers directly into your application, or you abstract it into an API, then have people integrate the API. So like similar to things you have like Alchemy or OpenSea API and all of that stuff. So I think the idea is you have to know the right time to use either approach, right? And that's basically what we'll talk about today. So it's like architectural decisions around app development in Web3. So yeah, as I mentioned earlier, you have the front end, then you have the middle, and you have the smart contract. So basically, what is the integration layer, or what integration layer are you going to use between your front end app, your React app, your Next app, and your smart contracts? So usually, direct smart contract integration is what is very popular, and that's why we have Ethers, VM, Web3.js. I think they're deprecated right now, but those are like the main forms of integration. And obviously, right now we've grown to have Privy, which now works with VM, but this time because Privy creates like an embedded wallet, so users can sign up with Google and all of that stuff. So in this this explanation or in this code snippet, what I tried to explain was how Privy and VM work together for direct integration. So here you have clients, like client does switching. So if you've used VM before, VM have like an initiator where you have like wallet clients to initiate like the setup with VM. So here you batch. So what this transaction does here is so you have gateway contracts. So the gateway contract in this instance is basically an off-ramp contract. So basically what you need is we need to be able to debit the user's account, fund our contract, then we send fiat to the user's bank account. Right. That's just what this does. So you can see the first call, we have the token address, which is the stable coin, right? You have the approve, the amount the user is trying to off-ramp, then that is approved for the contract to spend, and an order is created successfully. So once the order is created, that's done, and the user is able to off-ramp. Because if you look at here we have the message hash. Okay, so I think I tried to abstract a few things. So inside the message hash, that's where user's bank account and all of those will be hashed and to be de-encrypted on the contract side, and they're able to off-ramp basically. Right. So that's how an off-ramp logic would work if you're trying to build a simple off-ramp for users to basically debit the user and give them fiat. Right. So this gives you like complete visibility into the contract. You're closer to the metal, you know what's happening, you're not abstracting anything for the front end. This is important especially for like, certain form of integrations that you're trying to be sure, or the integrator is trying to be sure of what they're doing. Right. But for the API wrapper, this is also very important because we're getting to a point in Web3 where it's beginning to get adopted by mainstream tech firms or like tech companies, and most of them are not necessarily like Web3 native engineers, right? So what the API wrapper does, it helps simplify the integration process, so we don't have to like spend so much time trying to onboard them. That oh yeah, there's something called VM and something called ethers and all that stuff, or how to do APIs and all of that. So they just like integrate the APIs, and all of the magic happens on the back end. So what this looks like in real life is you have an endpoint, right? For instance, there's this Paycrest endpoint. So Paycrest is actually a real company that does off-ramps and on-ramps and all of that stuff, right? So you have your API key, you have your order data that contains, or the amount of USDC that about the off-ramps, network base and all of that, with the user's bank identity, the account number, their institution, and the rest, and you just pass all of that information into this endpoint, this /sender/orders, and what you get back is an object that have like the order ID and the receiver address. So in this instance, since the user is not connecting their wallet or anything, since just using an API, you get back a receiver address. So that receiver address, the user gets to send funds into that receiver address from like maybe their Binance or whatever, and they can then off-ramp. Because in this instance, they're not using like a MetaMask or any of those DeFi wallets, right? So what this does is that it hides like the complexities that are necessary to implement stuff like this. Banks or new banks or whichever of all of them can. So for instance, certain new banks, what they do is they allow you to send in stable coins into like an address, just like I just showed you, and the user gets USD on their neobank, and they can spend anywhere they are, right? So now that I think about it, I was thinking from a developer perspective, but also the user perspective, right, where regular users and regular developers can basically integrate into Web3 and are able to perform certain transactions. So just touch a bit on hybrid decentralization. So as I mentioned, because we're making this switch into like this sort of like mainstream adoption for Web3, in as much as you're thinking about APIs and smart contracts, you should think about using things like smart wallet integrations, gasless transactions through like Privy, and think about like batch operations and all of these things that basically make the UX simpler, right? I think Safe is one of the earliest users of like batch batch operations, right? And I think they do a really good job with it because they used to use like CalSwap, right, as their native swapping protocol. I think they've changed it now, but yeah, they used to use CalSwap at the time, and they used to have that batch operations. So I think here like a good comparison between the two. So developer speed is slower in initial setup if you're not a native sim, right? You need to like get conversant on what's going on. API wrapper is faster, full control, right? Because if you are doing directly, you know exactly what you're integrating. You can swap things out if necessary. So team expertise, direct interaction. The team has to, understand what's going on. They have to be Web3 native in terms of engineering. They have to know, okay, I have to approve first. I have to, approve the spender. I have to basically understand like the whole byte and everything that goes on with actual direct integration. But if they have like the right skills, then yeah, you can go ahead to still do the direct integration. Decentralization, truly decentralized. API wrappers, well, they're the backend, so not as decentralized. Yeah, there's gas fees and API fees and gas. Obviously, these can also be abstracted in certain ways. Like I mentioned, but with direct interaction, if you use a dynamic or a preview, you can also still pay gas fees for your users using like paymasters. So when should you use DeFi interactions and when should API interactions? So if you are building like very sensitive stuff, if I'm integrating a certain protocol, right, and I'm doing something very sensitive, I don't want to use APIs because I'm necessarily trusting them to do something or to like do the right thing and ensure they're not getting hacked, right? But if I integrate the protocol directly, I know at least I've removed a layer of error, at least on my end. Obviously, the team has strong Web3 expertise, custom interactions. So this custom interaction, the idea is if what you're building is new, right, you also want to integrate directly because it's easier to actually do. Because when you have the API wrappers, that's important because these are mostly like common, what do I call them? Common interactions like transfer, swap, NFT minting. Those are easier to like, they're standard operations that can be done easily. But when you have to do something very complex, many times, people prefer to just integrate directly. So obviously there are things like long-term control, flexibility, and the rest. I think before to skip. Okay, yeah. So I think the best practices is I'll share the slide later, just to save time for questions.
I've already shared the link in the live stream.
Oh, okay, that's good. But basically, right, those are like the two ways to integrate. But what I've noticed in the Web3 engineering space essentially is when teams are building their own in-house apps, many times they just integrate directly. But when they want to expose like a form of, they want third parties to integrate them, they mostly advise to use APIs because it's easier for them to like control, to KYC. For instance, certain companies or certain products don't allow you to off-ramp without KYC, and doing it on chain might be a little wonky or a little weird. So what they try to do many times is they have the contracts in their backend, so once you do the KYC, then you get access to APIs that can then off-ramp or do whatever they need to do, right? So that's a situation where people use APIs a lot, right? So but basically most of them do it now, like Alchemy, like papers I just showed you, several of these protocols. Because what I do right now is around like smart contract integration. So I'm seeing a lot of like teams pushing for APIs and SDKs also. I forgot to mention that. Yeah. So with SDKs, it's a little different. So what you do is you basically have the smart contract, then you write an SDK that performs action on that smart contract, right? So when people on the front end want to integrate with you, they use the SDK, then they pass in maybe the signer, and it does the same thing technically, but just using an SDK, just like simplified integration. So yes, I think we've been able to cover these two use cases and when to use it in your app. Thanks. Yeah, questions?
Questions, yeah. So I was just thinking, like, your answer might be Bonadox potentially, but I'm just saying,
unfortunately, it's not Bonadox yet. So Bonadox currently doesn't allow you to like take a smart contract and convert to an SDK. What you allowed you to do right now is, you import your smart contracts. You can call the smart contract methods just the thing we do on like the Block Explorer, right? And you can then write JavaScript using like 8,000 VM and then share that playground to somebody else. So whoever wants to integrate it can just look at your code that and all of that. But I think I'll be curious to know what that is that converts.
So I found it in 2021. But well, yeah, you can pull your smart contracts and then just upload the API and then just have the API based on your unique API, and it knows everything about like what your function is. So just like add a function and the API call, the parameters and things and all that.
So each API endpoint will be equivalent to each smart contract method.
So it's a generalized endpoint, and you have an ID for the smart contract that you've uploaded, and then you pass in the function, the method name of your smart contract, and then the parameters that would match that, right? And then the backend it understands all that. So it's just one generalized endpoint, and then the way it's able to decipher, what you're doing is based on that contract that you upload your smart contract API, and you get it back in that point. And now that the back end, it's got that all stored on RE and stuff like that, so it knows exactly how to basically orchestrate that.
Yeah.
But yeah,
Yeah, that's
exactly that use case.
yeah, that makes sense. I think I'm more curious about which tool will be able to convert, like the smart contracts to SDKs, but not just SDKs, but like because
SDK is just a wraparound API,
yeah.
right? So like, it really depends. Like, okay, do you need an SDK? Most people, once they kind of get into the weeds, they just want to like run part of the SDK and just use the API directly, right?
Yeah.
But having an SDK can just make it easier for people when they start. Like, when you put your npm or JavaScript or whatever, and you can just download it and run it, right? And sometimes for backend code, if you're really wrapping that API, then yeah, you've got some utility functions that like make it a lot easier, right? But basically all SDKs are wrappers around an API, right? So like you can just, in fact, if you ever annoyed the SDK's not working, just pull it apart.
Yeah.
Write your own SDK for that API, right?
Yeah, I guess that works actually. Yeah. Any more questions? Okay. Yeah, okay.
Thanks, David.
Thanks.
Our next speaker is JC, who's going to talk to us about reliable computing.
Let me see. Okay. Okay, sick. Which one do I connect?
Yeah. How does this work? Maybe go straight to HDMI.
How does?
Oh, okay.
Do you want to connect this one? Have you done this?
Testing.
Yeah, fantastic.
If you just put this on your pants.
Okay, put it on my pants. Okay, how long do I have?
You have you're the last speaker, but you have basically until 4 o'clock, so 20 minutes. So yeah. 20
Okay.
minutes, give or take.
Okay, amazing. Okay, let's go. Hi guys. What's up? Anyone was at Marquee last night?
This guy.
Oh shit, I'm the only one. Okay, cool. Yeah, so I'm gonna talk about interactive proof systems. How many of you heard of ZK, zero knowledge proof? Okay, so I'm probably gonna go through the intuition on how ZK even became a thing. So it really comes from this concept of interactive proofs, and I'll also maybe talk about how this relates to the project I'm working on. So I'm not going to shill too much. I'm going to be more educational in this talk. Yeah, so I'm going to give a quick intro to this concept of interactive proof systems, which is really the basis of zero knowledge proofs, and talk about how this actually relates to ZK SNUCs,
and also like for the optimizations like polynomial commitments, arithmetization, and also like zero knowledge machine learning, which is what we are essentially doing. But we don't necessarily always use ZK. So we kind of only want like the verifiability aspect most of the time. And if there's time, I'll show like the demos and some of the experiments that we have done. Okay, so why is verifiable computing matters? Why do you even want to verify things at all? So the problem is that there's a lot of bullshit in the world. So if you're going to token2049, you're probably going to hear a lot of bullshit. So like someone will be launching like, hey, buy my cat coin, buy my dog coin, and then like there's meme coins and shit. So you don't really want to bother with this kind of things, and you kind of want to filter out bullshit. And so how can you actually model this kind of like bullshit in general? And so there are many kind of risky and low trust environments in the world. Think of like things like smart contracts, war, and also yeah, it seems like schizophrenic mathematicians are the ones who came up with this idea. So yeah. So the guy who came up with this concept of interactive proof systems is, I can't pronounce his name. They have like so many like Laszlo Babai. So I remember his name as Babai. Yeah, but basically it came from this concept of Arthur games, and they use like the concept of graph isomorphisms and coin tosses. But we're gonna talk about applying it to Southeast Asia. Yeah, you recognize Zundamon and Shikoku Metan? Okay, great. I guess there are a lot of weeps in this place. Okay, so essentially we have two players. Think of it as a game. So you have a prover and a verifier. And so the prover has infinite computational power, but it can't be trusted. And so the verifier is now playing a game where it needs to kind of check whether this prover is not bullshitting them. Okay, so let's contextualize this in C. So you can think of this as a challenge response game. So in Pattaya, so if you go up to someone and say, "Are you lady boy?" "I'm not lady boy, nah." Okay, so the verifier is like, how can I know for sure? So yeah, really all of ZK can be, or even like interactive proof systems can be modeled as a challenge response game. So think of it as a game like you have multiple rounds and you kind of want to prove something, and so you can do things like index ring, finger ratio test, body fat percentage test, and period test or whatever, and you can do even more rounds. And so if the prover has enough valid answers after many challenges, you're probably not a ladyboy. Sorry, no hate to my ladyboy friends. Okay. So now we have this concept of challenge and responses. How do we actually formalize this system? Okay, so so if you think about like the initial the state of the problem, you can model this as some form of input string. And so in this case, the input string is just like it's kind of a set membership kind of thing, and this would consist of sexual dimorphic traits between male and female Homo sapiens. And you have things like random inputs. So the random inputs are now like the challenges that you essentially issue to the prover, and the prover will basically provide a response to the verifier. And you can model this interaction as a partial message history. So it's just like message 1, message 2, and so on. And so so essentially the verifier is a function that takes 3 variables. So the sigma, a symbol that is used in computational complexity, represents like the concept of an alphabet. So it's all the things that you can use to represent things in this game. And so at the end of like this process of providing the challenges and responses, you either accept or reject the answer. And this is essentially the formulation for the verifier function. And now we have to model the prover. And so the prover basically takes in 2 things. It has an input string, a partial message history, and also the message that it's going to send to the verifier. So so now we can define the interaction between the prover and the verifier, where essentially if it's even, so if you have 2 rounds, it means like it's a verifier's turn. So if it's 1 round, it's the prover's turn. And so it basically keeps alternating as many rounds as needed until you get like the right answer. And so in this case, the number of messages exchanged here are at most a polynomial length Pn. So it's a finite polynomial length. Okay, I'll stop here just to check whether you guys are like conscious or like not sleeping. So, so in this formulation over here, do you notice that we don't encode reject? Why is that the case? Anyone want to provide an answer?
Assume that reject is the default.
Not exactly. But yeah, that's also one way of like putting it. But yeah, it's kind of tied to PN because you have a finite amount of length. It will eventually terminate at some point. So it's not like a Turing machine where if it's not halting, like it's basically the answer is false. So okay, so in order to get a valid answer, you kind of have to repeat the rounds many times. And so you kind of want to do it as many times as possible to know for certain whether the prover is legit or crooked. So in computational complexity, we only deal with like 2 out of 3, but in practice, we kind of need it to be quite certain. Okay, so I don't think I can have enough time to cover these bonus questions, but there's this thing called like the PCP theorem, as well as and so this concept of interactive proof systems and this complexity class called IP. And an exercise here is to show that NP is proof within contained within IP itself. Okay, so now let's go into succinct zero-knowledge proofs. So how does this concept of challenge and response actually goes into this concept of like ZK SNUX? So I think people probably have talked a lot of ZK SNUX a lot, but they have actually not talked about the intuition on why this is even possible. So also in practice, we have been building a lot of ZK stuff in the blockchain space for the past few years, and it seems that zero knowledge is not always necessary. So sometimes you don't exactly need things to be private. So for example, in like L2s, most of the time you're not really using the zero knowledge property, but mostly like the succinctness of ZKPs, and which is why ZK rollups are actually not a good representation of the name, because you're not actually really having any ZK properties at all. And so we also found out that the concept of non-interactivity is really useful. And so I'll talk about how this non-interactivity is even possible at all. So ZK SNUX are indeed a special case of the IP complexity class, or interactive proof systems. So the issue with like the many challenge and response games that we were playing just now was that interactive proofs are very interactive, and so that's actually not a good thing if you're trying to do anything online. So if you played any game or some kind of MOBA like Dota 2, does anyone play Dota over here, or am I the only one? Okay, yes, there's one person who plays Dota. Okay, so the issue is that once someone goes AFK, like the whole thing goes to hell, correct? And so if you have like many rounds for a proof system, like it's going to be a pain in the ass to get the actual proof. And so Adi Shamia and I think Amos Fiat came up with this heuristic. And so the idea on how you make this interactive system non-interactive is that you have 2 assumptions. You have to assume that a random oracle function exists, and you have one-way functions. So in practice, this is actually not true. We'll see why this might potentially have some issues. But the idea in this case is to replace the challenges from the verifier with the hash function. So you can model the hash function as like a random oracle in this case, and so the hash function then encodes like the challenge and responses. And so remember like the random challenge R, and the input string which models like the problem that you're trying to solve, like graph isomorphism, so on, and the partial message history. You can essentially now model this whole thing as a single step process with a hash function. And so the verifier function that you see just now is now compressed to a single hash, which is very neat, provided the one-way function exists. So yeah, if you want more details, I left like links in my slide. So I'll send my slide somewhere, and you guys can view the references later on. So this is the catch, and so it turns out I think there was like a paper published last year called How to Prove False Statements and Practical Attacks on Fiat Shamir. So Fiat Shamir is not guaranteed to be safe, and it's also because if you're using hash function like SHA-256 or even things like Poseidon, which is typically used in ZK, they are not exactly one way or deterministic. So you can show that there's a collision. It's kind of over. So I think this is also an open question for the Poseidon hash function, which is used a lot in ZK. We don't actually know what is the cost to kind of find a collision in it. And also hash functions are not truly random. And so depending on the construction you have, you can potentially find essentially two proofs that verifies to the same witness value. But for most cases, like it's practical enough for use cases. And okay, so this is about the PCP stuff. This is related to the bonus question. I'll pass on this thing. Okay, so now we have the concept of ZK snugs. It's kind of really hard to express any kind of mathematical expression as ZK snugs, and it's still kind of useless right now. So at this point, we are essentially back in 2010. So it took us almost like 10 years. So when I was like a kid until now. So I heard about ZK snugs, and now it's actually practical. It's kind of insane. So there are a few things that are still missing. So we need things like arithmetization. So arithmetization is the process of turning a mathematical expression like 1 + 1 or a + b into a form that's suitable for like the ZK circuits. And also like the concept of PCP or probabilistic checkable proofs are still not very practical in practice. So they tend to have very large proof sizes, and also they take quite a while to generate. And so recently people came up with the concept of polynomial commitment scheme. So it's in a way of relaxation, and this is what is being used in practice. So have any one of you participated in a KZG ceremony of Ethereum? Okay, only one person, another person there. Amazing. Okay. So so KZG is an example of a polynomial commitment scheme as used for blobs right now on Ethereum. So this is kind of practical, but really it's built on 4 algorithms. And so the first phase is the setup phase, and essentially the ceremony does this process. And that's where you get the public params, where everyone knows about it, and you can use it to create a commitment and proof, and then use it to verify. So 4 steps: setup, commit, prove, verify, verify. And this is basically the gist of all the kinds of polynomial commitment scheme that exists. But where KZG is one of like a very common one. So Scroll actually has a very good blog post about this. I suggest that you read this if you are interested in this. But I'll roughly go through like the maths. Yeah, and so essentially you have like a generator function, and so this is the setup phase for Ethereum. You're essentially producing like many degrees of this generator function. And you have this value t, which is tau, which is a secret value. And so this is kind of like the random strings that you generate in the KZG ceremony, and you discard. You pass it to someone, generate, and discard. And so if everyone discards it, like you can't really find like the value of t. So I think the security factor is 1 out of n. If at least one person discards it, like t would be secret. And next. Yeah, so this is basically like the commitment phase. So you essentially produce, let's say you have this polynomial function phi. You essentially run the generator on top of phi to produce this commitment. And then you have another evaluation like phi a equals b. You can then generate a proof on that with the same generator function. Yeah, and essentially the verify process, it dwells down to this. You're essentially verifying a bilinear mapping in a polynomial space. I shan't go through the details about this because I think it's probably another like math course. But essentially, like you have 4 steps. And now you can essentially verify information using polynomials. So the next other thing, which is also quite fascinating, is that now you have this concept of KZG. You have essentially like many polynomial equations. And so now you have this concept of arithmetization. So let's say I have a function like a plus b, and I want to encode this polynomial. Like, how do we do this? So Phong introduced this concept of like it stands for a really long name. I can't remember what it was. But the idea is that it can essentially represent like generic mathematical equations in this form, where you have essentially switches, inputs, and also constant terms. And so you can view this basically as a circuit. And so this is how the circuit looks like. So you have like constant terms, and so your constants in the circuits are public values, and your x in this in this setup are essentially private values, and the s symbols over here represents switches. So you can think of it as electrical circuits. Which is why like the concept of arithmetic circuits are being used. Like they call it circuits. And so now with something like this, you can essentially express the concept of addition. For example, if you want to do like a plus b or L plus r equals 0, you essentially just put 1, 1, 0 on x and r, and put 0 on the constant, and you essentially get the concept of 0. And so, because it's in this form, you can essentially put it in your ZK, your polynomial-based ZK circuit quite easily. And so you have the concept of multiplication, and also you can simply assign constants to this form. And here's where it gets interesting. You can also do things like non-linearities like ReLU functions. So for example, you want to express the concept of max 0 and x, you can do something like this, where you essentially you can use like the right switch and essentially allow any kind of input to go via like XR in this case. And so now you have the concept of addition, multiplication, and nonlinearities. You kind of have like a basic block of a neural network. And so this is essentially like the basis of like the project that I'm doing called Ezekiel. And so now with the concept of Plonkish arithmetization and polynomial commitment schemes, you're now able to express like neural networks. So this is kind of handy. So if you want to write a neural network, you can essentially use things like TensorFlow or PyTorch and convert into this like format called ONNX. And so we are heavily reliant on ONNX to produce ZKPs. So instead of writing like your circuits in like things like Circom or a specialized language, you can essentially use AI or like the same AI programs that you use, which is kind of handy because you don't need to think about the ZK elements in this case. You just think of it as math. And so you can kind of think of ZKPs in this case as a way of increasing the compute expressivity of the blockchain. So consider if you have like smart contracts, you have like gas limits, you have there are some things that you can't really do. Let's say if you have like very weird operations or even like exponentials on the blockchain, it's kind of hard to do that. Or even like summation. Summation is and finding averages. So you can do like a time-weighted average sequence, but then it requires like additional cost. So with like the concept of ZKPs, you have the idea of like computing something off-chain, putting it on-chain, which is the basis of ZK rollups. And you also have like the concept of privacy as well as compression. And so it's kind of a really handy tool for how you can increase what blockchains can actually do. In particular, Ethereum right now, because we mostly built it on ETH. So I'll go through like a demo to kind of make this kind of concrete. So I have about 3 minutes left. So I read this previously, but essentially, yeah. So for example, I have a neural network defined as such. Like if you can see, the model is essentially a sequence of linear layers, and you have like a forward pass in this format. You can essentially train it, and you can then ZK the neural network by calling this library called Ezekiel, which is a library that we built. And so back to like the 3 steps. So you have setup. So in this case, we split it up into 3 steps, like get SRS, compile circuit, and setup. But essentially, they are the same setup steps in the polynomial commitment scheme. And you can then run proof and verify. And so all the complicated like mathematical stuff that you would have to deal with is now encapsulated in this program and abstracted from you. And so the cool part about this is that you now get this generated Halo 2 verifier. So in the past, you would have to write this by hand. If you wrote something in Circom, you would still have to write the verifier by hand. So we basically built a tool to kind of generate like the verification function on Solidity directly. And all you need to do is call verify proof. And that's it. And it makes it really easy to think about the business logic of how you can use ZK on-chain versus the technicalities of ZK. Yeah, I'll go through some interesting examples. I don't think I have time to go through all the experiments. Yeah, but there's one experiment that's like live right now. So it started as my hackathon project at ETH Denver. It's called CockSwap. It stands for Cleverly Optimized and Computed Swaps at ETH Denver. Oh yeah, it was like Singapore first, and then I did at ETH Denver, like on Balancer instead. So you can think of this. So we are working very closely with Balancer right now. And so you can think of it as like AMM's on-chain on steroids. There are a bunch of things which are possible, but right now we are focused specifically on dynamic fees on-chain. So I think one interesting use case for ZK right now is you have many static parameters on-chain, and you might want to change it. So you can go via a DAO, but that's sometimes too slow. Like trying to get people to sign things on-chain is kind of hard. And so this is where like AI would be really useful. And having the AI be verifiable is even more important. Suppose if you have like a pool that has $200 million in value, you don't want some random AI to be changing stuff. And so we have essentially some incentivized pool. Why is it unincentivized? Yeah, it's incentivized. Oh wait, it's unincentivized. Yes, amazing. Yeah, so we actually have two pools that this is part of the experiments that we did, and so we actually found a class of models which are able to increase the fee collected by LPs. So we can essentially defray impermanent loss on chain right now. So the difference I think is it's like roughly about 20%. So on static fees we are getting around 34%, and on the dynamic fee pool, we are getting like things like 49%. And so we have like a proposal live coming soon. It's actually live on Balancer right now, and so we'll probably be managing the RVE pool and be doing other kind of fund management stuff with like things like Balancer. And so this is kind of like the design space which we are at. You have something on-chain that you want to change, something that might be static, and you want to make it dynamic. This is where things like ZK and verifiable AI is really very useful for at the moment. And there's quite a lot of value that I think is still unlockable, because there's so many things that are static simply because it's troublesome to change on the smart contract. Yeah, I'll basically end here. And so this is the Discord, and if you want to contact me, I'm HenloJCM on TG and on X. Yeah, this is I think like way too fast, so sorry if I went too quickly. Any questions? Hello.
Thanks for fantastic sharing, and I want to ask like based on like in the interactive system, so the final result of the system is based on like the result of each round, right? So is there any specific like measurement or metrics that you can prove that it's enough, is the times of the round that is sufficient to prove the result?
Oh yeah, so I think for there are some examples, right? So the example that they use is called a public coin. It's like a public coin flip. So for example, I want to know whether the coin is biased or not biased. So let's say it's truly random. I basically ask the guys to keep flipping the coin, and if it's like close to 50%, like it means like it's the coin is fair. Otherwise, it's not fair. So the biased coin example is probably like the best way. So if I flip it once, if it's heads, I still do not know. If I flip it second time, it's tails, maybe 50-50, but I still do not know for sure. So I keep flipping many more times until I get like a fair indication that it's like 50-50 after like maybe 1,000 rounds. I hope this example works. Okay.
So I guess you're talking about upgradable contracts, right? So you're talking about putting in the AI to replace the DAO. So in
So it's not exactly completely upgradable. So in this case, we are specifically dealing with parameters. So the AIs that we are doing in this case are not LLMs. So LLMs tend to be quite vulnerable. So we have actually. So I think there were people talking about trying to snuck large language models, but we found them to be quite impractical and also like vulnerable to attacks. It's actually doable at the moment. So we are able to snuck GPT-2, and I think it's possible to snuck GPT-3. But I think the question is, how do you prevent like hallucination attacks or like prompt injection, which tends to happen. And if there's like $200 million of value and you have like a prompt injectable like LLM that is controlling it, that's disastrous. So we are mostly dealing with smaller models, like think of things like decision trees or even things like logistic regression based models where the behavior is understandable. And so yes, using those things to change specific values. So it's very similar to what something like Gauntlet does. So I'm not sure anyone here use DeFi or knows of Gauntlet or Chaos Labs. So they're essentially like involved with calculating things like LTV parameters on Aave. So for example, on Aave, like how do you decide that the LTV should be 75%? So people like Gauntlet will create data science models to say that 75% is probably good for this like pool, and then through governance, they will just set the value on Aave through a DAO vote.
For liquidity depth?
Liquidity depth, in what sense?
So that's when you liquidate your position, you can liquidate it correctly without too much slippage.
Yeah, I guess like finding like the optimal liquidation point is also important. So there's essentially a lot of this kind of parameters on chain that it might be good if they can be automated. So right now it's just like a value that is fixed, like for example 75%. And it's typically more conservative, and so they do not change this like for years. So which is kind of a great business. You just do the work once and you charge like the protocol $1 million and you just like fuck off. It's kind of a great business to do. But in this case, like if you want to squeeze in more value, like this is having some kind of keeper function that calculates the value based on some kind of protocol data is kind of important. I hope I answered the question, or if I'm not clear, like let me know.
Is it possible to put an agent in it to automate the thing?
Agent in what sense? So I guess like in this way, like the fee managers, you can consider it as an agent, but not a very smart one. So its main job is just to figure out what are the best fees. If no other questions, feel free to just ping me and I'll share the slides. So I think I left a bunch of like papers and maths, which kind of go through the story of like interactive proof and ZK in a more concise fashion, because I feel like most references are kind of overwhelming, and so I feel like people do not really like have the time to read through all of these things. So I created a quick crash course and compilation of all the relevant materials over here.
All right, thank you.
Okay.
So while Rahman is getting up, stick around, right?
Anyway, yeah. Thanks everyone for coming. Thanks for speakers for speaking. This has been awesome, I think. So we're just gonna do a picture with everyone together, and then another one with the speakers only. Or first with the speakers, and then
either way.
Maybe since there are fewer speakers, we can do speakers first, and then everyone else. And so we have time until 5 p.m. to mix and mingle, say hi, shake everyone's